Welcome back to ECE 442-542. You have 6 hours to do your TCE if you haven't already, and I do need your help. We're under 50% in terms of a response rate, and I'm assuming you continue to get emails saying please fill out your TCE or not. If you haven't yet filled it out, I think they just continue to send. I don't have anything to do with that. All I can see is that 47% of the class this morning had done the TCE. So if you know some friends in the class, you've already done yours, if you could suggest that they do it in the next few hours, it's due by 11:59 this evening, I would really appreciate that. It is helpful for me. We talked a little bit offline about the final exam review session. We're tentatively saying that's at 5 o'clock on Monday, the 11th, and it's tentatively in ECE 530. I will try to firm that up or verify that and send out an email and maybe post it on the D2L website as that day gets a little bit closer. Special office hours, I'll try to stick to what I already have in terms of office hours, but here's an extra one. Next Tuesday, I'll give you a 2-hour time slot from 2 to 4 in the afternoon on the 12th of May. That usually a Tuesday. We haven't worried about office hours all semester. I'll go ahead and open that up. Our final exam is on 2 days thereafter on Thursday at 1 o'clock, and it's in this room. So don't get all mixed up in where are we, what's going on. You come to this room, we'll have the same strategy as we've had before. We'll go quickly over some of the process for the final exam, and then we will start looking at this laundry list of state space design techniques. You should be able to, for homework number 8, which was that on the announcement? Okay, homework 8 is due tomorrow. So you have about 30 hours to finish homework 8. If you're doing the project, that's due tonight. That's due at 11:59 if you're in 542. So you have some back-to-back. The homework number 8 is optional. You don't have to complete that, but you will need that material for the final exam. And the final exam, you will have some state space. We're going to talk about full state feedback. We'll talk about full state feedback with a non-zero reference input, and then we'll just keep going with these ideas. We'll look at integral control. And what did that mean when we were dealing with transfer function design? When I said integral control, what do you immediately think about happening? When I say, oh, we have integral control or an integrator, pure integrator in our system, what did that correspond to when we were doing transfer function-based design? You see this x right at z equal to 1. We're basically going to do that. We will force that to be true. We will augment our system dynamics to make that happen. And why did we like pure integrators in that forward path? They helped us with steady state error, didn't they? And we'll look at how we can actually force that to happen in a state space setting. Force a pure integrator in the forward path. We will basically add on some more dynamics. We'll add a pole at z equal to 1 is really all we're doing. But we will put it in a particular location. And then we will show what that means. That will augment our system dynamics. We'll add one more state to our already existing state vector. We had 10 state vector components to begin with. Now we've added another one. We've augmented our state space to where we now have 11 states. And that one additional state will be that pure integrator state. And that will hopefully be clear from what we talk about. So that's full state feedback with integral control. The last two deal with trying to eliminate the assumption that we have the full state vector available to measure. Let's say that you now have some system dynamics. Maybe it's a engine, and one of your state variables is the temperature of your engine, and you don't have a sensor that actually is going to measure that, so you don't have that state variable available to you. Now what do you do? And you've done this state space design. Well, we'll talk about an estimator. And the estimators that we'll talk about are really just copies of the model system that we think we have already. We'll simply duplicate that and then interconnect it with what we do have and see how to build a full state estimator. If we now have a full state estimator, now that's saying that we have estimates of all of these state variables. Why don't we use those as if they were the real state variables? That's this full state estimator with feedback. We've already figured out how to adjust the gain, the full state feedback gain. Let's see what happens. And then we will spend a little bit more time on this integral control. Wow, really? We are here until your homework is due. No, until your project is due this evening. We are here until 11:59 this evening. We need to cover all of these blue lines, blue line specials. So we'll look at augmented system matrices, talk about where do we get the full state feedback gain, full state estimator, full order compensator. Wow, I'm tired just looking at that list. Here's the final exam information. Here's the process that I hope allows you to not be quite so anxious when you approach the final. The final will be comprehensive. That almost goes without saying. By this point in the semester, I could ask you one question with 15 parts, and it would then depend on everything that's trickled back to the start of the semester. The exam, you get one more sheet of notes, front and back, if you want. We've had 3 exams so far. This is the 4th exam. It's a 2-hour exam. You can have an additional 2 pages for your transform tables. That could be this Laplace and Z transform table where you have the different columns, one for Laplace and one for Z, and then you have the second page is maybe your Laplace transform theorems, maybe not your pairs of transforms. You can bring in all your drafting equipment if you want, your protractor, your compass, your straight edge, your ruler. You can bring a graphing calculator. What you can't have are notes. In addition, you've already got 6 pages. That's enough to shuffle through. No books, no computer, no cell phone, no neighbor, etc. Should be about the same. It's just you now have more problems. If each problem has 4 parts, you have 60 things to think about. So you've got 2 things a minute, or 2 minutes a thing. So you want this material to just be oozing out of your pores when you enter in on Thursday. It's the last day of finals. Ready to go. 1 to 3. Does anyone have a final exam after the final here? Maybe all those that are not in attendance are studying for that final. But according to this collection, this sample, it looks like that will be your last final. So on your way out the door, make sure the door is closed before you start whooping and celebrating so you don't disturb the others that are still taking the final. But try not to think too much about the after the final until you're complete, okay? Focus, focus. Questions on the final exam? Let's then slide through some of this material. When you hear state space, I want you to almost immediately be able to write down these equations. or sketch this block diagram. And this D is not like the other blocks. I hope it's clear that this block is actually a bank of delays, meaning X is now a vector with many components if you needed them, and you're just delaying those to get to the output of that delay block. But then X at time step L plus 1 in that block diagram is exactly what you have in the coupled set of difference equations up above in green. X at time L plus 1 is phi X of L plus gamma U of L. How do you tell the open loop dynamics of that system? If you wanted to describe, oh, what's the behavior of your system in the open loop, somebody asked that on an interview question, how would you answer that? The phi matrix, right? SpongeBob. I should have made phi look more square. That's a square matrix, isn't it? And what about phi do you look at to give the dynamics? You look at the eigenvalues, and those are the poles of your system if you computed capital G of Z. That you should be very comfortable with. You would then compute the eigenvalues of phi, and then depending on where those are positioned or located in the complex Z-plane, that tells you something about the dynamics. If they are all in the unit circle, and somebody said, well, you've got 10 poles, you've got 10 X's, and they're all in the unit circle, which ones would you look at to sort of determine the dominant behavior? Is that question clear? Do you understand what you're looking for? If you had a unit circle and I had 10 X's in that unit circle, which of those X's, all 10, which ones would you look at if you said, oh, I need to focus on the dominant behavior of this system? Where would those X's live that are contributing to the dominant behavior of your system dynamics? Okay. The comment was the ones with the largest radius. Again, we're assuming we're inside the unit circle. If we had one pole outside the unit circle, obviously that would dominate and it would go unstable. You wouldn't have any kind of nice behavior. You would smell something burning up, or it would just go unbounded. It wouldn't be good, would it? It'd be an uncomfortable scenario. But if you have them all 10 inside the unit circle, now you're looking at the ones with the largest radius, preferably in the right half plane closer to z equal 1. If they were complex conjugates, you would look at the ones that are conjugate pairs. Once you have conjugate pairs, now what could you do? You need to know how to find, when I do this, when I cover my heart, where I know you don't think I have a heart, but pretend I have a heart. What system property is governed by that heart shape inside the unit circle? Percent overshoot. What about the concentric circles? What do you associate with these collapsing or concentric circles? What property? Settling time. What about the angle that those poles make? That governs their speed, isn't it? We related that to peak time. So there's a lot of information that you can extract by just being given or handed that system representation. And that's in the open loop. And you should be able to Not that you would need to repeat this derivation, but you should be very comfortable if somebody asks you to, on a napkin, you could derive that transfer function from the state space representation and give them capital G of Z. That's just the output matrix H times Zi minus phi inverse times gamma. And the poles of G of Z are exactly the eigenvalues of this system matrix phi, the open loop system matrix. You may not be happy with that system's behavior. And so we talked about, when we have a state space representation, applying full state feedback. In a block diagram, that red line that's feeding back to form your input into the system, the input u at time L, is just minus k x of L. What's the main assumption that you're making with this scenario? What are you assuming is true? It's been a long day. What assumption are we making for that block diagram? And now when you go back and watch this video, you'll just see Tharp acting silly and going and sitting in C19. Bingo. Yes, no. There's actually a couple of assumptions that we're making. The one that I originally thought of was what? Where are you going to collect that feedback? Are you using the output, or are you using the state? It's the state, isn't it? You're assuming you have every one of those state variables available to you. You're measuring each one of those state variable components, scaling those by whatever values are in your feedback gain matrix K, and you're combining those in such a way to form your input into the system, and you inject that information in. Now you have closed loop dynamic behavior. If you weren't happy with the dynamics before, hopefully you can use K to force better dynamics. The other assumption that I am assuming, if I can say you can arbitrarily locate the closed loop poles, now what assumption am I making? Controllability. Is that system completely controllable? And you should know how to compute that. The controllability matrix, and if we have one input, now you have a square controllability matrix. You can just compute the determinant of that matrix. To check controllability. That was a regulator problem. That was basically, with full state feedback, nothing else. This is like putting some masses and springs together and pulling those masses in different positions and releasing them. It's an initial condition. It's a regulator problem. You're trying to drive everything to this equilibrium position of 0. That may not be what you want in most control configurations. You may want to inject an external or a reference input. You want to add on to that full state feedback this additional or this second input piece, which is a reference input, scaled by some value, capital N sub 1. That leads to the following block diagram. It's identical to what you had above, except now you have this blue addition, which is the reference input. And I think what you'll want to do when you get home is maybe even start scratching these block diagrams. If you're just sort of sitting and watching, now you probably want to say, oh, if I had a reference input with full state, what does that mean in terms of an equation? That's this multicolored U, green equal red minus kx plus blue N sub 1R. It's these different pieces, but your input into the system is made up of full state feedback with a reference input. And what does that mean? Well, you can sketch it in a block diagram form. To me, that makes a little bit more intuitive behavior than just writing the equations. Now you sort of see how the different pieces and parts go together. That's the benefit of sketching this block diagram. And again, this is not a matrix, is it? That's just a bank of delays, that D block in all of these block diagrams. And you could then start working through those equations. But that block diagram sort of shows you how you are changing the dynamics, because now there's not just phi being fed back, now you're feeding back K as some linear combination of your states. And that now comes into this closed loop system matrix phi sub C right there, by combining your terms that are scaling the state vector X. Now you could determine the dominant poles in phi sub C. Again, what are you computing if you wanted to know the dynamics of this closed loop system? Again, you're just looking at the eigenvalues of capital phi sub C, the closed loop dynamics. Do you remember how we might have adjusted N sub 1? Here is our closed loop system written in the frequency domain, or trying to find a transfer function based on that second equation on the screen right now. You z-transform it, you linearly combine, and you solve for this transfer function between the reference input R and the output Y. And now T sub C of Z is this entire collection of matrices. How would you select capital N sub 1? Or what are some reasons behind selecting N sub 1? If you wiggle R, what do you want to happen to Y in general? If you turn R to 5, what are you probably wanting Y to do? Probably follow that reference and go to 5 with particular dynamic behavior. If that's the case, if you turn R to 5 and Y goes to 5, how do you pick capital N sub 1? Or how would you describe that? If you had to write a sentence and I said, how do you select N sub 1 in this system configuration, what could you say? What do you know about the gain characteristics of that closed loop system? If you turn R to 12 and Y goes to 12 in the steady state, what do you know you have property-wise in capital T sub C of Z in your closed loop transfer function? What is happening? If I say gain and then I start saying what frequency are you interested in, right? A low frequency, DC. DC is where what value of Z is representative of DC in the frequency domain for discrete time systems. 1. You now evaluate capital T sub C of Z at Z equal to 1, and you want that to equal 1. If N sub 1 is yet to be determined, you can try to fix that expression to equal 1 by the appropriate choice of capital N sub 1. You pick N sub 1 to give you a DC gain of 1. And that's possible, very easy to do, when you have a single input, single output system. Then you have gamma that's one column wide. H is one row tall. And this messy looking formula down below is found with little z equal to 1. If you had 10 states, what's the dimension on capital I in the denominator of that expression? It's 10 by 10, isn't it? Identity matrix that's 10 by 10. So yes, you would have to invert a 10 by 10 matrix, but you post-multiply by a 10 by 1 vector. Now you have another 10 by 1 vector, which gets pre-multiplied by a 1 by 10 row. Now you have this inner product of that, and it boils down to a 1 by 1 matrix or a scalar, even though you may have had started with 10 state variables. As long as you have one input and one output, you could then compute a number for capital N sub 1. I just like building block diagrams, don't I? That may not give you a very robust solution. If we go back here, and you've now selected capital N sub 1 to give you a DC gain of 1 in capital T sub C of Z, what's going to happen if, my system coming off the manufacturing line, my phi matrix was not like what I thought it was? There's some uncertainty in phi, or there's some uncertainty in gamma, or there's some uncertainty in H, in my measurement matrix, or in my input matrix, how my input is injected into my system. If there's uncertainty in that, then the choice that you made for N sub 1 may not actually give you a DC gain of 1. If phi varies, or gamma varies, or H varies. I told it to go to 5 and it went to 4.276. Where did that come from? Well, there was maybe some uncertainty between what you thought your system was modeled as and what your true system was. The way that we attacked that before was, this integrator was sort of nice. Having that pure integrator in our system allowed some slop in our poles and zero locations, and we could still always go to the value. For a constant input, we could always go to that value at the output. That's the reason we might want to now approach a problem by introducing an integrator into our state space representation or configuration. Right now, if you mentally erase all of that blue stuff, we have what we had before, don't we? We just have the full state feedback with the full state feedback gain matrix K. If phi was different from what we thought it was, then we may not be getting the accuracy that we want in our tracking. If we put it in a 4, maybe we get a 3 out. So we say, I don't like that. If I put in a 4, I want to get 4 out. And I know the way to do that is to introduce a pure integrator in my forward path of my system. Phi could have had a pole at the origin, but you probably moved that by the choice of K. I'm sorry, phi may have had a pole at 1, and you may have moved that with your choice of phi, or of K. I told you it's been a long day. I better go sit in C1 for a while. Ooh, that might have come through the video or the audio. So now I have this integrator. Do you see that that's just introducing another pole at z equal 1? And look how it's introduced. It's in the forward path. And you are introducing one more gain, this k sub I. You're gaining that state variable that you've now introduced. The state variable is x sub I, and that is integrating this error signal E, which, just to make the expressions a little bit cleaner later, I've actually created an error signal that's a little different than what we've always done before. Look at what E is. It's now Y minus R. Typically, we've said the error is R minus Y. Well, here, because of the way we are now putting gains in here, here's a negative sign and there's a negative sign, we really want Y to be coming back positive at that point, so that we now have this minus sign in the minus k sub I. And that will filter out in a minute. But the error is now the difference between the reference and the output. And if we pick capital K appropriately and capital K sub I appropriately, how would we pick those? Where would we want our closed loop poles to be? Inside the unit circle. That question is not hard. It's just figuring out how to do that, and I'll show you how you can do that in a little bit. But now you just treat this like another state space full state feedback design. It's just you have a little bit bigger state. That state has now grown in dimension by one variable, x sub I. And what's the reason for this again? Why did we put that integrator in there? What do we want E over there on the right-hand side of that, or just at the output of that summing junction on the far left? What do we want E to do eventually? We would like to drive that to 0. And that integrator, if we get everything in this closed loop to be inside the unit circle, then we can guarantee that we're going to drive E to 0. If E is 0, then Y will track R. Even though there could be some changes in phi, gamma, and H between what we designed for and the true system. And that's a little different. We're paying a little bit more of a price for this than that N sub 1, just the reference input gain. Now we've added in one more piece of dynamics, an integrator into our system, a memory location in a discrete time system. And our control signal, U, Coming out of that second summing junction is simply a linear combination of what we have been doing all along, a full state feedback, minus capital K x at time L, minus a gain on that integrator state, x sub I at time L. That's now our control signal. Questions on that? I know we're going through this pretty quick, aren't we? But I want you to appreciate the power of an integrator. That's important, and you need to know that for this class, especially when you're designing what? A PI controller, a PID. That I is giving you this integrator. You need to be able to play with integrators there. Here, I'm extending that concept to the state space design domain. When you graduate, when you finish school, somebody might start talking about doing state space designs, and they may say, oh, I need an integrator. And you go, kind of remember back in May of 2015 talking about an integrator. I was falling asleep during that class, but let me go see if I can find the notes. And this is what you might cook up. The reason being, you want to drive your steady state error to 0. Even though you might have some uncertainty in your system matrices, gamma, phi, and h. Now, what I want to do, I want to stay in state space design territory, but now I want to move towards eliminating the assumption that I can go in and physically measure that full state in practice. Maybe I can't do that. Maybe I can't go in. Maybe I don't want to buy a sensor that will give me all the different state variables, where your state might be position, velocity, voltage, current, pressure, temperature. Maybe you don't want all of those sensors floating around. Maybe you just want to measure one or two, or maybe one in this class. Y is typically 1. You linearly combine all of those states in your H matrix, and now you have one output. Can we still use some of these strategies that we've talked about? And the answer, the quick answer is yes. We don't have to throw everything away, even though maybe all what we can measure is the output. And here's now what we want to do. We want to talk about how do we build an estimator, or somebody might call this an observer. This estimator is now going to try to produce or generate an estimate of each of these state variables. And we'll call that x hat at time L. X is the true system state. We are going to try to build an estimator that will basically produce a copy of x of L as a function of time. If we're going to do that, it sort of makes sense to just copy the system dynamics. So if you can virtually erase or not see the blue lines, look at the two black pieces. You have the top piece, which think of that as the true system. And then you have the bottom piece. And what's the bottom piece? It looks exactly like the top piece, doesn't it? In terms of gamma, phi, and h. But the one down below is the one that you have in your computer or in your microprocessor. That's a copy of what you think is in the real system. Here is, let's say, the system, the true system. And here is what we are trying to copy. The lower one is what we could actually build up. You could write those difference equations in an algorithm in your computer. That's just a bunch of linear difference equations. That could just be a for loop saying x at time step now is a linear combination of these x hats and u's. The problem is if we started the real system, the one up above, a little bit offset from our model, then y and y hat may not be the same. But if we could start both of these at the same position and with the same internal states, if x was x hat and we applied the same u to both and we had exactly the same phis, gammas, and h's, then we would expect y and y hat to be the same. In reality, we know that's not going to be the case. There's probably going to be some mismatch in our system matrices between gamma, phis, and h, and we probably can't start these exactly in sync, meaning the position of our system might be at 1 centimeter and our estimator we don't know, so we just start it at 0. What we want to do, though, is force x hat to approach x. And the way that we do that is we compare our outputs. What do we physically have available to us? Now we're saying we can't go in and physically measure x in the top system. We can only measure the output y, and we have access to the input u. Meaning we can now compare the system output with this estimator output. We can compare those by taking their difference. We can say y of L minus y hat of L. That generates an error signal, which I'm calling E sub y. We use that error signal to basically tickle our estimator in an appropriate way to make x hat approach x. We're not going to go into how we would select L sub p, but L sub p is just like designing capital K before. It's just a eigenvalue placement problem. And this would be the estimator dynamics. You would pick L sub p to locate your estimator poles to be fast so that that speed tells you how x hat is going to approach x. So once you reach steady state and these two systems, the real system and your estimator, are singing together, x hat is locked onto x. That's the idea. That's this full state estimator. That's what we want, and we would pick L sub p to give us those dynamics. Then what do we do? Well, we probably want to control the system. Here, we weren't changing the system behavior at all, were we? We weren't trying to adjust the dynamics of that top system. We're not feeding back anything into U based on what's going on in the system. We probably want to change the system dynamics. And now that we have a copy of the system and x hat is tracking x, why don't we just use x hat as if it were the true state? We knew what we wanted to adjust, how we wanted to use the true state to feed back to form our input. Let's now use x hat as if it were the true state. This is now a full order estimator, that's the bottom, with estimator feedback. Now you have an estimator problem to solve. That's to figure out L sub p. And you have a full state feedback problem to solve. That's capital K. What's the relationship between K and L sub p? you probably adjust the dynamics of your estimator to be faster than your closed loop system dynamics. You want X hat to go to X quicker than maybe Y hat is moving to its final destination, or how Y is moving to its final destination. What you're really after is controlling that upper system. You want Y to have some behavior, desired behavior. You now have two different designs to carry out, the choice of L sub P and the choice of K. You need to be able to do the K design on the final and on homework 8. You won't need to do the L sub P design on the final, obviously. I hope that's obvious. But I want you to understand that you can now push a lot of this a good distance after this semester is over, if needed. You now have the tools to start moving quite far beyond where we were able to get to this semester. Are there questions on what we've done? Yes. Pardon? So the capital K here is doing what it's been doing so far this semester for you. It's adjusting the closed loop system behavior when you have full state feedback. Capital K is assuming your system is completely controllable, and it's now allowing you to adjust the open loop poles and push those or move those to desired closed loop pole locations. That's what K is doing. And the beauty of this design is that you can actually solve these problems in a decoupled manner. You can solve for the estimator gain L sub P separate from the K, the full state feedback gain. And you can still just put them in this, and they will give you these results consistent with the two independent designs. The K, the full state feedback gain matrix, in this approach, you pick that, you select that just like you've done in the earlier design that you will need to know for the final, which is right there. You pick K just like you picked it here, as if you had access to the full state. That's how you pick K. So the goal is to have this system, the dynamics of this system, behave the way you want it to behave. And that's related to your heart, your bullseye, and your angle, typically. And you might select your dominant poles in the closed loop to have some certain percent overshoot, settling time, and peak time. And then where would you put all the other closed loop poles? Just as sort of an inside strategy for this class. Where have we agreed? Inside the unit circle, but if the others are dominating, where do you put, let's say you have 5 closed loop poles and you've located 2 of those consistent with your heart, target, and angle. Those located 2. That was percent overshoot, settling time, and peak time. Gave you 2 of the 5. Where do you put those other 3? Do you want those to be slower than the first 2 that you picked? You need them faster, don't you? You want the first 2 to dominate. And dominate in this class means those are the slow ones. Those dominate in time the behavior. That's what we mean by dominant behavior. Those are the slowest ones, and those you probably want to be fast. relative to the open loop behavior. So you could, we've sort of agreed in this class, we may want those other three right at the origin. That'd be the quickest way to pick them. You have all sorts of options. You have an infinite number of options, but you probably want those in terms of settling time to be, what, maybe a factor of 5 faster than your dominant ones? If they're not, then they're starting to sort of color or shape the dominant dynamics. So in terms of concentric circles, you would want your faster poles to be inside a circle in the unit circle that's maybe a factor of 5 times faster than the dominant ones that you've already located. And that's how you pick capital K. Is that helping? Then, can I make things even more complicated? Now we have the estimator to worry about. Well, you've already picked K. Now the estimator is this L sub P. And L sub P is similar to K in that it's some matrix. It's a gain matrix. But now you pick it to be faster than all of your other poles in the closed loop because you want the estimator to get where it needs to go before you start acting like the where you're at is the true state. It's hard to grasp in 5 minutes. Okay, I apologize for that, but I want you to start thinking about this or sort of having a clue as to what somebody might be talking about if they say, oh, I need you to build a common filter. Oh, I need you to build an estimator. I need you to build an observer. Ooh, let's see, something about the end, the last lecture in 442, 542, we were talking something about that. Well, that's what this is about. Now you would have, let's say that all of your poles in the closed loop system were maybe at a diameter, or I'm sorry, a radius in the unit circle of 0.5 or larger. Now you would probably locate your estimator poles, the L sub P gain you would pick to be inside that small circle. You want them faster so that you have X hat going to X much more rapidly than Y is eventually settling to a final value. The reason for that is if you had X hat going to X slower than you were trying to command X, it's never going to catch up. That's poor illustration, but if you now have X hat and it's trying to catch up with X, but its dynamics are slower than X's, you're going to have a mess in terms of trying to control your system because you're using X hat to control the whole system. You don't have access to X. So you want X hat to be quickly approaching X so that X and X hat are locked on, and now X hat looks like X. You can use it as if it were X. That's why L sub P would be picked to make the dynamics of your estimator faster than the closed loop system dynamics given by K. The fire hose is on. Okay? I'm spraying you with a big, we're not in California. Okay? We're being a little bit liberal with our water today in terms of the content. But we'll have a good punchline at the end. Okay? But let's now go through maybe in a little bit more depth what integral control might look like. So now we sort of stepped back again into this integral control. Why do we want integral control? Do you remember? Zero steady state error. Integrators are good for giving us good steady state accuracy. What we want to do now is figure out how do we change this into something that we already know how to play with. Can we put this into a state space representation that makes us feel warm and fuzzy? What's the warm and fuzzy state space representation we know? X at time L plus 1 is equal to phi x of L plus gamma u of L. That makes us feel good, right? Can we make this look something like that? And that's what we're trying to do. But now our phi matrix will be a little different. Our gamma matrix will be a little different. But if we can put it into that structure, then we're back to where we started. And we can be happy. That's where we're trying to go now. So let's, with this block diagram, figure out how to make that happen. We're going to try to have full state and integral gains incorporated into this. So let's now see if we can implement this or find a way that's consistent with what we've talked about this semester last week in trying to find the original K, the full state feedback gain matrix. Can we use that same strategy to find K sub I and K hat, where K hat is now what we used to call K? It's kind of a curve, but bear with me. What we want to do is figure out how do we model that integrator in the time domain. This is a review. This is a review for the final. If I gave you that piece that's circled in yellow and said, give me a difference equation for that piece in my block diagram, you should be able to do that. That's just going from the frequency domain into the time domain. And that's our square dance, one of our square dances, right? How do you start with a transfer function and get to the time domain difference equations? That's what we want to do because we already know the time domain of the black piece. That's just our normal expression. Let's now see if we can go from frequency domain to time domain for that little piece, and here's that little piece extracted from the big block diagram. Does that look like what was circled in yellow before? There's my transfer function, 1 over z minus 1. Does that look like this transfer function between e and x sub I? That's the connection I'm trying to make. I want to put that into the time domain. That now should look just like that. There's e, there's x sub I, and they are related by this transfer function, 1 over z minus 1. Where's the pole in that transfer function? Right at z equal 1, right where we want it. That's our integrator. Now we want to take this into the time domain. How have we done that before? Our output is capital X sub I of z. That's equal to a transfer function times an input. And here our input is E, the error signal. We can multiply both sides by the denominator expression, which is z minus 1. Is everybody still with me? This should be just a review. Now do you see how you can take this into the time domain? Remember what z is as an operator. Z is just an advance in the time domain. Just like playing with s's in the Laplace, now you should be somewhat comfortable playing with z's. I'm doing this in small steps. We now have that z and 1 minus 1 distributed across capital X sub I. That's our new variable that we want to take into the time domain. And there we have it. We have little x sub I at time step n plus 1 minus little x sub I at n. Oh, I told you I wouldn't use n's, didn't I? N is saved for Nevada. That really changed things, didn't it? Didn't. But at least you're not confused with n being the dimension of the state vector. Now our time variable is L, and this you should feel fine. What is this doing? This takes the air now, adds it to the state of that integrator now, and that generates the integrator's output one time step into the future. And what's an integrator doing? If you had to say, go back and teach Math 1, Calculus 1, and or maybe it's 2 that you start talking about integrators, isn't it? Maybe math, first semester calculus, you're always just differentiating. Second semester, you're integrating. What's an integrator do? It's the area under a curve, isn't it? That's all you're doing. This is a numerical way of doing that. You're finding the area under this air curve. That's all this is. You're just adding up that air. And if you drive the air to 0, that's going to be a good thing. That's what you're wanting to do. Now you have to remember how we defined that air back in our block diagram. Remember, I kind of did a little bit of a different behavior here. Here was the plus from our output, and then we subtracted R from that. So our air signal E was Y minus R. And that's what I'm using here. E is Y minus R. But what's Y? That's the output, but that's related to our state through the output equation H. Y is just Hx, and R is R. So we're subtracting that from Hx, which is just Y. Oh. What's that about? Have to go back and erase, don't I? At least you're following that much. Might as well just keep my eraser handy. The air signal now is just the output minus the reference signal, and the output is just H times X minus R. So that now if I use that in E right here, which is right here, that's what the right-hand side is doing. This is now E of L. So X, little x sub I at L plus 1 is just X sub I, the time step before, plus the air. And the air, we've just made it, we've constructed it in our block diagram to simply be Y minus R, and Y is just Hx. Now we basically have the equations that we need. This is one state variable component. That's the dynamics of one state variable component. It's written in terms of the state and the new little component x sub I and the reference input R. We can use that together with little x equal phi x plus gamma u. So what I'm going to say, I'm saying we can augment the integral dynamics. These are the integral dynamics right here. onto the original dynamics. There, the integral dynamics, that's the same as the boxed equation, isn't it? Little x sub I at time step L plus 1 is little x sub I plus hx minus r. And our original system dynamics were just x at time step L plus 1 is equal to phi x of L plus gamma u of L. We comfortable with those two equations? Those x's may not be the same size, are they? Little x, think of that as 10 rows tall. How tall is little x sub I? How many integrators did we introduce? One, didn't we? So little x sub I is just one variable, whereas x is 10 rows, potentially. Let's now put that into some matrices, and that's what I'm doing here. I'm creating an augmented state vector. I had x originally. I just added on top of that. Obviously, I'm hungry. So here's my analogy. I went to Baskin-Robbins and I had a two-state ice cream cone. I had strawberry and vanilla. Those are my two states. What did I do? I put one more state. What kind of ice cream do you like? Strawberry? No, I already had that, didn't I? So now I could have another flavor, pistachio. So I now have strawberry, vanilla, pistachio as my integrator. You see what I'm doing with my state variables? I had two to begin with. I asked for a third scoop. That was my x sub I. That's now my new state variable. That's my augmented state variable. It's now 3 flavors tall. I started with 2 flavors and I added one more. I could have started with 10 and added one more. I could have started with 5. That's my original x, and I add one more. Is it clear what that augmented state vector is doing, what it looks like? Now you see this and you go, I'm going to build an ice cream cone. That's okay. That's really what you're doing. You're just augmenting what you started with. And what you started with is whatever your original system dynamics demanded. If it was a 10th order system, your little x was 10 rows tall. And now you're just adding one more to that to make it 11 tall in total. But if you now have this 11 tall total, do you see that I can write the first row, little x sub I at time L plus 1, in terms of little x sub I and x, u, and r? That's what I want to do. Is that top row correct? It needs to be just like the difference equation a couple of rows above the matrices. Little x sub I at time, we're doing more than building ice cream cones. At time step L plus 1 is x sub I of L plus hx of L, no u, little u, not you. You need to be here for the final. You need to be here for the final. Which is when? Thursday at 1. Just saying. Okay. What's the dimension of phi bar? How big is it? It's now little Nevada plus 1 by little Nevada plus 1. It stayed square, didn't it? We still have a SpongeBob, right? We haven't changed the shape of our system matrix. Is the bottom block row consistent with the row, the difference equation just above the matrix representation? We've just written it in this augmented system, state space system representation. Now do you see that I can define that new square matrix as my new augmented system matrix? That's now a capital phi bar. And my input matrix is now 11 rows tall, and if I had one input before, it's still one column wide. And it's a 0 on top of my original gamma. And I'm going to call that gamma bar. And now I have, how big is that 0 in the last column on the right? Is it 1 by 1? Bless you. How big is that 0 in the rightmost column in that augmented system matrix representation? How wide is that 0? How many R's do you have? We just assumed one reference input, didn't we? Didn't we? So how wide is that 0? How many columns wide is that 0? It's just one. It has to be compatible with R, doesn't it? You're multiplying each of those rows in that big 0 by whatever R is, and there's only one R, so you can only have one column of zeros. How many rows tall is that 0 matrix? It's compatible with little x of L plus 1, and we started with Nevada components in x sub L plus 1, or 10, or 5, or whatever. That 0 matrix on the far right is 10 rows tall and one column wide. Do you see that? So you would, if you were building this up in reality, that 0 becomes a 0 matrix that's 10 rows tall and one column wide. Do you see how we would build a full state controller now, full state feedback controller? We want to change the dynamics of phi bar with the choice of little u, the input. And we have access to x sub I and x. We're assuming full state feedback. Now we have k hat and k sub I from this. What's the dimension on k bar? If we have one input, k bar is how many rows tall? Can you represent it with your fingers on your hands? If, let's say, our state was 10 to begin with. We have one row if we have one input, right? And how many columns is k bar? It's 11 columns wide. What's the dimension of k sub I? It's one row tall. How many columns wide is k sub I? It's compatible with little x sub I. And how many components were in little x sub I? 1. So k sub I is 1 by 1. K hat is 1 by 10. That's the original size of our full state feedback gain matrix when we didn't augment in the integrator. So here's the words that we'll finish with. Here's our control law design. Using integral control, we would place the poles of phi bar minus gamma bar k bar with the choice of k bar. which is 1 by n plus 1 in dimension. Once you've found k-bar, then you simply partition k-bar. You just pull off the very first component of this 1 by 11 row vector, and that becomes your k sub I. The following 10 columns make up k hat, which you now put into this block diagram. K sub I goes right there in the front. That's a 1 by 1 scalar gain. K hat is this row vector in the bottom feedback path from X. And that's how you could produce integral control such that you wiggle R, Y is going to track it. If R is a constant, you'll have zero steady state error between R and Y. What do you need to know? The material for homework 8. You won't need to know integral control or full state estimator, but you will need to know full state feedback and with a reference input, little n sub 1, which was basically way back in the first 6 minutes of today's lecture. But I didn't want to tell you that, or you would have zoned out even more before now. Thank you. Don't forget to do your TCEs if you haven't.